Yesterday, we learned about series circuits. Now, these circuits look like this, and the reason we call them series circuits is because everything is in a row. There is one path for all of the electrons to travel down, and there's not any sort of diversity. Now, today, we're going to talk about parallel circuits, which will look something like this. We call these parallel because of these parallel lines that are formed. All of our resistors are on these parallel lines. Now, they don't necessarily have to be parallel lines. Obviously, they're wires and they can be skewed different directions, but we use that name because when we draw it out, we have this view of these parallel lines. And these parallel lines are separate tracks that the electrons can go down. So they can go up and go through resistor 1 or resistor 2 or resistor 3. We're going to deal with these a lot of the same way we dealt with series circuits, but the rules are a little bit different when dealing with parallel. Now, last lesson we talked a bit about how in series, voltage sources add together, and that's how we get multi-cell batteries. Now, in parallel, they don't add together at all. Actually, when they're in parallel, there's no change in the voltage. Essentially what happens is some charge comes out of the top one, some comes out of the middle one, some comes out of the bottom one. So the strain on each battery is a little bit less, but the overall voltage that's created is going to be the voltage of the highest voltage battery source. So these three in together, if they're all the same voltage, they're each going to contribute equal amounts of current, but the total voltage is just going to be the voltage of one of the batteries. So here is a parallel circuit, and it has three resistors in it, R1, R2, and R3. Now, just like before in our series circuits, we were able to figure out the equivalent resistance, and with series, remember that we added all of those resistors together. Here in parallel circuits, we're able to do the same thing, but the math is a little bit more difficult. So the equation for adding these together is going to be 1 over R1 plus 1 over R2 plus 1 over R3 plus ... is equal to 1 over R total. Now, so this ... here means, obviously, if you have 4 resistors, you would make it plus 1 over R4. 5, you make it plus 1 over R5. However many you have in parallel, you take the reciprocal, so 1 over, and then you add all those up, and you get 1 over R total. Now, this can be simplified using summation notation. So for those of you who don't really know what summation notation is, it basically means you put this sigma, which means sum together. So you add up all of these parts, 1 over Rn. So any number, so R1, R2, R3, Rn, add them all up is going to be equal to 1 over R total. So let's do that for this circuit. So this is the equation up here on top that we just discovered, or that I just taught you, and then this down here is with all of these values plugged in. Now, some of you may be thinking, how do we solve this, Mr. Halberstadt? There's too many radicals, Mr. Halberstadt. That R is in the denominator, Mr. Halberstadt. So if you really are concerned about the math on this, you can just plug these into your calculators. So add these three fractions up and then put it to the negative 1/2 power, or do 1 divided by the answer. You all can solve with the calculator. I'm going to go ahead and solve this analytically. First, we get a common denominator. Luckily, we have that 60 there, and these are nice multiples of 60. So we get 3 over 60 plus 2 over 60 plus 1 over 60. This gives us 6 over 60, which is 1/10, which is equal to 1 over our total resistance. From there, we can find fairly easily that our resistance total is going to be equal to 10 ohms. Don't forget your units. So what that means is that this whole collection of resistors, even though we have a 20 and a 30 and a 60, when they're all combined together, it reduces down to a 6 ohm resistor. Now notice that total resistance is much smaller than each individual resistance, but it makes sense because if you have 3 different pathways to water to flow down, so remember all of our current is water. If we have 3 different pathways for current to flow down, that's like having one really wide pathway. So there's not a lot of resistance because there's a lot of different paths that the current can take to get back to the negative terminal of the battery. So now that we've talked about how to deal with resistors in parallel, let's look at how our other values are affected by this type of circuit. Now, when dealing with parallel circuits, the way we look at voltage drops is we actually ignore the other resistors in the circuit. So if we're focusing on the voltage drop across R1, we can just ignore R2 and R3. So if asked to find the voltage drop across R1 in this circuit, we just can say, okay, we have 6 volts coming out of here. We know that when we end up back at this end, we're going to end up with 0 volts. And so our circuit has to have all of our voltage dropped across this resistor. Because remember, any voltage that you put in has to drop before you get back to the end. So we come up with 6 volts, it's going to drop to 0 and then come back at 0. If we want to do a similar thing and look at what's on R3, we just block out the lower 2 resistors. So we just take this, put it here, block these resistors out, and so the voltage drop across R3 is also going to be 6 volts. Because again, we start with 6, we drop it across this resistor, we have to drop everything, and so our voltage comes back in at 0. So that's a 6 volt drop across this resistor. Now, something you may want to think about is how easy it becomes now to figure out what the voltage drop is across any resistors in parallel. The voltage drop is going to be the same for all 3 of these resistors. VR1 is equal to VR2 is equal to VR3, which is equal to 6. All of the voltage drops across all of these resistors is the same. Current is where these sort of circuits become more difficult. Now I'm going to split the remaining amount of page that I have in half, so that way we can talk about one method to figure out the current, and then we can compare it to a different method. So the first way we're going to talk about current is going to be what we're going to call the long way, and that's by doing each of these little loops independently. So one loop here, and then 1/3 loop here. So we start with our basic equation, V equals IR, and then we just rearrange it so we serve for the current. So in this example, we're going to be using I equals V over R a lot. So we substitute in our first set of values, so our voltage across our first resistor, which is going to be 6, and we have to divide by the resistance of our first resistor, which is 20. This gives us 6 over 20, which gives us 0.3 amps. Now let's do the same process, but for the second resistor. We have a current or a voltage of 6 again, a resistance of 30. That gets us a current of 0.2 amps. Now for the last resistor, we have a voltage of 6, a resistance of 60. The final current is 0.1 amps. So let's take a moment and talk about what each of these currents mean. I1 of 0.3 means that at this point here, right before our second resistor, our current is 0.3. I2 says that at this point here, right before our second resistor, our current is 0.2, and here it is 0.1. Also same on the other side because these bits of wire in front of and behind the resistors are in series. So this whole area right here is where we have that current. But where does it break down in these in-between areas? I want you all to pause the video for a second and just think about what would be happening in these in-between areas. What did you come up with? So what's actually going on is these currents are all added together. So if we are looking at the total current, and when I say total current, that means the current coming out of the battery and the current that's going to come back in the battery, we can add these 3 currents together. So our total current is 0.6 amps. So that means coming out of this corner here, we have 0.6 amps. And then when we get to this junction here, the current splits. and 0.3 of the amps go across R1, and the remaining 0.3 continue up here, then 0.2 go here, and 0.1 continues up around R3. So if you want, at this point, you just have to ignore the current going through R1 and just add together R2 and R3. 0.3 amps coming through this wire right here. Now I know you all didn't forget that I said earlier that this method was the more difficult method. So let's take a look at what the easier method would be. And in order to do the easier method, we have to remember something from our previous slides. That's right, our old total resistance of 10 ohms. So let's take that old total resistance and look at what our current would be if we just assumed that these three resistors were all combined to one of the total resistance. We use a similar setup from what we did before. The V equals IR is the same, and then we look at our total current is equal to our total voltage over our total resistance. Same equation as up here, but instead of looking at over a certain resistor, we're looking over the whole circuit. And would you look at that? If we use this method with the total resistance and then figure out the current for the total thing, it equals our total current from the previous method, looking at each resistor. So this just tells us that there's consistency with how we've decided to do this. The voltage drop is going to be the same as the total voltage, and all of our currents are going to add together or separate apart at junctions, so they'll separate here and then come back together here. We will talk a lot more about this total voltage idea and this separating of current at junctions in the next lesson. Now, power is going to be pretty easy, but I want to just remind you how power works and get you comfortable using power in both series and parallel circuits. So in this instance, we can look at the power consumed by the entire circuit or by just one resistor. So we use the current for the whole circuit and the voltage for the whole circuit to figure out the power of the whole circuit. So 0.6 times 6, which gives us 3.6 watts. Now, I just want to go into a little bit about watts. Remember, watts are joules per second. A lot of students have been getting watts and energy and work mixed up. Remember, watts is joules per second. So it's a unit of how much time or how much energy is consumed in a given amount of time. So let's look at what happens for our power of R1. So if we look at the power of R1, again, it is going to be the current of R1 times the voltage of R1, which is 0.3 times 6, which gives 1.8 watts. Now, if you were to find the power consumed by each of these resistors and add them all up, it would be the power consumed by the total circuit, which is good because if that didn't happen, we would have power coming from somewhere that we don't really know about and can't really explain. I will leave the exercise of finding the power in all three resistors and adding them up to you to do if you don't believe me that it all adds up to 3.6 watts.